Very quickly introducing what we're going to cover today, right? So today we're going to talk about sorting. And why is sorting important? I mean, sorting is essentially nothing but arranging data that you have in a particular order, right? For example, if I have a few numbers, I could say I want to arrange them in an increasing order. Or if I have people, let's say I want to arrange them in the decreasing order of their height or increasing order of their height, etc. The ordering, because you are able to order something, helps you in a lot of things. For example, sorting might then help you do binary search on that data if you want to look for something. Or if I give you queries around, hey, tell me how many numbers are bigger than a specific number. That also, I mean, if the array is sorted, you can just look for the index of the first element bigger, and then you know how many numbers are bigger, etc. So sorting helps in those contexts if it is ordered. In fact, most NoSQL DBs, they actually try to maintain data in a sorted form. Sorted set is what it is called, because it makes searching for data, looking for data, doing a bunch of analysis on data easier and easier, right? So today, we're going to just to elaborate, we're not going to talk about searching. I'm going to talk more about sorting. Sorting is arranging data in a particular order, right? So for example, if let's say give you 5 numbers, I give you numbers, let's say 5, 10, 3, 2, and 8. These are numbers in no particular order, right? Now, if I say arrange these numbers in an increasing order, where the smallest number comes at the front of the list and so forth, that part is called sorting. So, I mean, if you sort this, then you'll have 2, 3, 5, 8, and 10. It's an arrangement of the given numbers so that they are in some particular form or order. As I said, like the reason why it is important is because it helps you do a bunch of different kind of operations on the data fairly quickly if what you have is sorted. And I gave the example of NoSQL databases where they maintain data in sorted sets because it lets them do a bunch of different kind of queries in a sorted form. In fact, we will talk about some form of MapReduce when we go to system design modules. There also you'll see like a lot of things are generated in sorted forms because it allows for certain more operations to happen later on. Does everybody understand like what sorting is? So maybe like the way I would explain sorting is taking just like in binary search, I took the real world example of searching in a dictionary, what we normally do in real life. I'm again going to be taking the example, a real life example of what we might have done in our lives before, right? All of us went to school, and in school we were made to stand in increasing order of our heights. Now, let's take that example, which is I have a class full of people and I want to arrange them in increasing order of their height. Right now, assume they are standing in some random order. What are the different ways in which I can actually arrange them in increasing order of their height? And I'm going to take various sort of approaches I would have taken. And then I would sort of map it to what that approach is in real life. So approach one could be that I ask everybody to come one by one. And I mean, let's say if I have a few people already standing in the line, let's say I have few people that I've already arranged in the line. And let's say there is this new guy with this height that comes. In fact, it is better to imagine, I mean, maybe I can write the height of each of those individuals. Let me just write the height. So imagine I had somebody with height 1, 5, 12, and 27 already in the line. Somebody with height 7 comes. One thing which I can do is I can find the right position for this person, which is between 5 and 12. And I insert 7 there, which means then I'll have 1, 5, 7 here. And then 12 and 27, I'll push one space back. Right? So 12 comes here, 27 comes here, right? And then as people keep coming, let's say there is a person called 32. I'll figure out where 32 should lie here. I'll figure out 32 should come here. I'll insert 32 here. Everything up after 32 would be pushed one space back to make space for 32. Here, there is nothing. This is called insertion sort. This technique where I get numbers I figure out what is the right location for them. I can do that through binary search, or I can do that through a linear scan. Either is fine. Once I find out what their location should be, I shift all of the other numbers one space to their right and then insert this new number at the new location. Now, that is called insertion sort. If I have to write the approach for this or the steps for this, basically assume that I am maintaining my sorted array in, let's say, sorted array list. That's a sorted list, which is initially empty. And imagine I keep getting a few numbers, right? What I do is I start from the end of this list. For example, here, if I had 1, 5, 12, and 27, and I wanted to insert 7, I'll start from the end. Is 7 already bigger than 27? It is not. So what I would do is I'll shift 27 one space to its right. So imagine this was the array. I have one space left here, so I'll shift 27 to its right. So 27 comes here. Then I go and again check 12. Is 7 bigger than 12? No, it is not. So I'll shift 12 to one space to its right. 12 comes here. Then I check the next number, which is 5. Is 7 bigger than 5? Yes. That means this is the location of 7 and I insert it here. I keep doing this with every new number that I encounter, and that makes for what is known as insertion sort. What is the best case complexity here? Best case time complexity here. And what is worst case time complexity here? Best case for sorting. Order 1 would be the time complexity of inserting a new element, best case, right? Because you start with 7, you'll find that, let's say the new element that we are inserting in this new array, let's say that is 32. Best case is I look at the first element and I find that 32 is bigger than that, and therefore 32 just gets inserted here. It is for the addition of the last, like the new element. Order 1 is the best thing that you can do, but you'll have to add n such elements. So therefore, if you do order 1 for n elements, you'll end up with order n best case complexity. So in the best case, insertion sort will take order n time. What is the worst case? When do we get the worst case? What is the worst case, and in what kind of data would we get worst case? If the array was reverse sorted, which means if, let's say, I was giving you numbers, I first give you number 5, you insert 5. Then I give you 4. You insert 4 here, right? Because you'll have to shift 5 1. Then I give you 3. You'll figure out that actually 3 is smaller, so you'll shift 5 here, then you'll shift 4 here, and then 3 comes here. Then I give you 2. You'll again shift 5 here, you'll shift 4 here, you'll shift 3 here, and then 2 will come here. And then again, you'll do one more shift and to get 1 in if 1 is the next number, right? This ends up taking, for the first number, you take 1 step. For the second number, you take 2 steps. For the third number, you take 3. And for the fourth number, 4 and 5 and 6 and so forth. So this becomes almost order of n square. So worst case, this might take order of n square when the numbers are sorted in decreasing order. A very interesting question, which is, does the time complexity affect if we take linked list? There are 2 parts here, right? Like one is, there are 2 things that we're looking for. One is, what is the right index where this new number should go? And the second is shifting greater numbers to make space. One place right. So your linked list will save you on this time. So this time will become 0. However, finding this 1 in a linked list, because you can't really jump to a random location, you'll have to do a linear scan to figure out where the number should occur. Right? So that might still end up taking order of n square, because searching for the right index, the step number 1, that might end up taking order n. You can't apply binary search in linked list because you can't just jump to a random location in the linked list. Right now, the way I explained insertion sort was that you were getting a stream of numbers and then you're sort of sorting it by putting them in the right location. Now, whatever I said, that can also be applied to an existing array as well. Let me explain. Right now, the way I detailed insertion sort is by saying that, you know what, like 5, I'm getting 5, then I'm getting 4, then I'm getting 3, then 2, then 1. Imagine I was already given an array, right? So imagine I had the array as, let's say 5, 8, 3, 2, 18, hypothetically, right? And I asked you to sort this array in place without using extra memory. I do not want to use any extra memory. Can you sort this array without using extra memory? Insertion sort. So I don't again have the flexibility of creating a new array. I am doing this in place. How do we do that in place? Even when you're doing in place, imagine I start from 5, right? So first I'll start with 5. I'll say I only have to sort this. 5 is the new number that I've gotten, right? So I have one place, 5 is the new number I've gotten. Obviously it will go at this position. So 5 comes here. Then I go to the second number. And I say, let's put this in a temporary variable. Temp is equal to 8. Now 8 is the new number I'm trying to insert in the first two locations, right? So first I'll compare with 5. Is 8 already bigger than 5? Yes, it is. So it will come here. Then I look at sorting the first three numbers. I pick 3. So I delete 3 from here, imagine. And it is, this 3 is the new number to be inserted. So first I check with 8. Is 3 bigger than 8? No, it is not. So 8 will come here. Is 3 bigger than 5? No, it is not. So 5 will come here. And then 3 gets inserted here. So now if you look, I mean, by now I have the first 3 numbers sorted. Now I'll take this number 2, which is I'm trying to sort the first 4 numbers. I'll take the new number 2 and imagine that 2 is the new number that I was getting. So I put this in a temporary variable. I'll do the same comparison. Is 8? No. So 8 comes here. Is 2 bigger than 5? No. So 5 comes here. Is 2 bigger than 3? No. So 3 comes here. And then 2 comes here. And then finally 18 is bigger than 8. So 18 will directly come here. Does that make sense? So same approach. All I'm doing is I'm saving on the additional space if an array is given to me already. The worst case time complexity is still the same. Nothing has changed in the approach. I'm just using the same space that was there in the array instead of creating a new array. Okay, so if we apply binary search for position, it will contain more computations, right? Finding plus swapping. Yes. If you do apply binary search, you'll first take log n time to find the right location. And then in worst case, order n extra time to create the space. I mean, right shifting all of the elements to create space for this other element, right? So it will end up taking n plus log n every single step instead of just n every single step. So this log n is additional. Overall time complexity will still remain n square because you'll do this n times. So instead of n into n, you'll get n into n plus log n, which is basically n square plus n log n, which is still order of n square. But why do that? I mean, why do this additional operation? Why not just start from the end? You have to shift the bigger elements one step to the right anyway. So just start from the end, shift the elements to the right, and then like fit the element wherever you find the first place. All right, everything clear till now? So that is one way in which you would sort, let's say, your classmates, right? The second approach that I have is, let's say I have an array, right? Like let's say the same array. I had, in fact, let me go with the original 5, 10, 3, 2, 8. So 5, 10, 3, 2, 8. And I put this in an array. Now what I know is that in the sorted array, the smallest number has to come at the beginning of the array. Do we all agree with that? Smallest number has to come at the beginning of the array, right? So one thing that I can do, which is not very optimal, but still works. It is every single time I look at what is the minimum in my given array. For example, if I run this loop, I'll figure out that 2 is the minimum. I say, okay, great. If 2 is the minimum, let me push 2 to the beginning of the array. So 2 comes here. And then I can just swap it with 5. So 5 comes at the place of 2. So when I do this, 2 comes here, 5 comes here. Now what I know is that now 2 is at the right position. I only have to sort the remaining 4 elements. And I repeat the process. For the remaining 4 elements, I again look for the minimum. Find 3. So I swap 10 with 3. And then I sort the last 3 elements. And then again, like I look for the minimum 5. I put 5 here and then so forth, right? The only downside of this approach, while this approach works, The only downside is it is order of n square no matter what the input. So in the best case, worst case, everything is order of n square. The good thing with insertion sort was that there is a case where the best case was order n. So therefore the average performance could have been better. If we do this, it is always order of n square. I mean, basically the steps were find minimum. 2 is put in start of array and then start plus plus. That was the approach. If the array is already sorted, even then, to find the minimum in the array, you'll have to look at all n elements. So every single time finding the element is taking you order n, right? So that approach is a precursor to BubbleSort. So while this approach works, the question is, can we do something so that if the array is already sorted, then we don't have to go through all of the elements all over again, right? Like every single time finding the minimum takes me a lot of time. How do we decide when to break? Check whether the array is already sorted or not. Let me maybe give some other case, right? So insertion sort will still be order n if, let's say, only one element was not in its right position. Every other element was in the right position. For example, if the array was, let's say, 1, 2, 3, 4, 0. The array is just very simply some random elements. BubbleSort is a variation of exactly this. BubbleSort is, as the name suggests, it is like bubbling something to the top, right? So what you do is you compare all adjacent elements one by one. And wherever you have a pair of numbers, so what you do is, for example, let's say people are standing in some random order in the line, right? So for example, I have people standing as 5, 10, 3, 2, 8. Let me just write it like this: 5, 10, 3, 2, 8. My objective is somehow bubble the smallest number 2 to the top. So what I do is I say the last person standing in the line, hey, you compare yourself against the next person to you. You obviously know how to compare yourself against the next person. You can check your height versus the other person's height. Obviously, if you're standing behind and you're smaller, then you should swap yourself, right? So I say 8, look at 2. If you're smaller than 2, then swap yourself. 8 says I'm not smaller. Great. Then I say 2. Look at the next person ahead of you. If you're smaller than that, then swap. And I do see like 2 is smaller than 3, so I swap. So 3 comes here, 2 comes here. Then I say 2, swap yourself against the next person if the next person is smaller. I figure out 2 is actually smaller than 10. Sure, I mean, should get swapped. So 2 comes here, 10 comes here. And then I again say 2. Again, compare yourself against 5. If you're smaller, swap yourself. So 2 again gets compared with 5. 5 comes here, 2 comes here. So what has happened in this one order n loop? The smallest number has bubbled itself to the top of the array. This is why, I mean, because the smallest element is bubbling to the top, it is called BubbleSort. Even this approach in the worst case will take order n square. There is one difference here though. If there are no swaps that happen all throughout in this order n loop, then we just stop there. Which means if the array was already sorted, then we would not do the next iteration. We'll keep doing the next iteration as long as there is swap happening. So let me elaborate again. What happens is, imagine you're standing in the line. I start from the last person. I say, compare yourself against your neighbor. You compare yourself against the neighbor. If you are smaller, then you swap yourself. And then you do that till the start of the array. One thing which is guaranteed in this loop, whatever is the smallest number will bubble up to the top of the array. Then you're left with sorting only the remaining part of the array. And you also know if there is any iteration where I went from the last person to the first person, there was no swap happening between the neighbors, then I know that elements are already in the increasing order. I can just stop. I do the same process again. Now 2 I don't care about. I already know 2 is in the right position for the remaining elements. So I again start from 8. I say 8, are you bigger than 3? 8 will say, yes, I am. And I say 3, are you bigger than 10? No, I'm not. So we'll swap. 3 comes here, 10 comes here. 3, are you bigger than 5? You're not. So sure, I mean, then let's again swap. So 3 comes here, 5 comes here. Again, if you see, 3 has bubbled up to the top, which was the next smallest element. And then you're left with sorting only the last 3 elements. Any iteration where you don't have any swaps, your array is already sorted, you can just stop. Since we had 1 or more swaps in the first traversal, we'll start again from 8, but will not go till 2. 2 will be ignored. I mean, the first element is already sorted, so we'll be ignored. We'll stop here. Now that in the second iteration, we know that the first 2 elements are fixed, we'll start again from 8, but we will stop at after 3. I mean, we'll not look at 3 and 2 anymore because we know that they are in the right position. Every single iteration, what is happening is the smallest element is bubbling to the top. And any single iteration, I know that there is no swap that has happened. I can just break. And therefore, I do have a best case complexity, which is if the array was already sorted, I will do an order n iteration to figure out are there any swaps. But post that order n iteration, I can just break. Or if I reach a stage where, intermediary stage, where let's say I did these and then the remaining numbers were already sorted, then also I'll just break, right? So I'm not really spending time sorting if the array is already sorted. Does that make sense? Let me actually write the pseudocode for this. What I'm going to do is I'm going to start. So here's my inner loop, right? So I'm going to start from the last element. Let's say there is a j that starts from n minus 1, goes to, imagine I'm doing a loop of I from 0 to whatever. I'll tell you what 0 to whatever is. It goes to I. Imagine that like numbers till I are sorted. Right now, nothing is sorted. So n minus 1 to I. What I do is here I compare a of j with a of j minus 1. Now I know that in the right order, a of j should be bigger. So if it is smaller, if there are two numbers where the second number is smaller, then obviously they should be swapped. The second number, if it is smaller, if this is smaller, then they should be swapped because they are not in the right order. So I just say swap a of j, comma a of j minus 1, right? By the end of this, a of I will have the smallest element anyhow. I is starting from 0. A of I will have smallest element anyhow. I also keep track of one variable here. Has there any swap that has happened? Let's say there is a flag, which is initially 0. Whenever there is a swap that happens, I make flag as 1. If at the end of it, if I see that flag is 0, then I just break, which means this element was already sorted. There is no need to look at other elements. And then I goes from 0 to n minus 1. Yeah, sorry, this is I plus 1. Correct. So again, like what is happening in the algorithm is the smallest element is bubbling to the top, and you're just taking in the process, making sure that if the remaining elements are in the right place, there was no swap, then the element is array is already sorted. So let's just break. Yeah, actually we don't need the n minus 1. When we come to n minus 1, I plus 1 would anyhow, this j loop will not run. So I can just do n minus 2. Again, let's look at what is the best and worst case complexity of this algorithm. Best case is order n, which is my array was already sorted or almost sorted. And then, I do this iteration, flag becomes 0, I break. And the worst case is when it is reverse sorted. So every single time I have to do a lot of these swaps, and it is actually order of n square. All right. So this is, by the way, called BubbleSort. Find the smallest element, move it to the beginning. This is called SelectionSort. In SelectionSort as well, it's what we were discussing, where we were selecting the smallest element and moving it to the beginning of the array. That is SelectionSort. The reason why we are discussing this is these are intuitive ways of how we think about sorting, and the technique can come into use later on. Let's do a dry run with BubbleSort just to see the best case, right? So imagine I asked you to sort this array 1, 2, 3, 4, 5. Imagine this was my input, correct? SelectionSort is sort of an greedy algorithm, because what you're doing is you're saying that I know the smallest element should come at the beginning, so let's find the smallest element. You put it in the beginning, and then you sort the remaining array. Let me, however, show how the BubbleSort is still best case order n. SelectionSort, by the way, we can also make order n in one case. I'll also go over that. SelectionSort, just slight variation, and it can become best case order n. Let's first look at how it becomes order n best case in BubbleSort. Imagine this was your input, right? You start with I as 0. I is 0. J, your flag is also 0. J basically goes from, so you have your index 1, 2, 3, 4. J will start with 4 and it will go till 1, 4 till 1. And what do you do? Every single time you just compare A of J with A of J minus 1. So you check, is 5 less than 4? The answer will be no. So then you move on to the next J. So from 4 you will go to 3. From 4 you will go to 3. Then you compare 4 with 3. Is 4 less than 3? No. Then you will compare 3 with the previous element. Is 3 less than 2? No. Is 2 less than 1? No. So at no point this if condition gets executed. So there is no swap, and therefore flag never becomes equal to 1. So when this loop finishes, when the J loop finishes, you come to the point where flag is still 0 and therefore you break. So just after the first iteration with I 0, you end up breaking because you figured out there was no swap involved in my array. So my array is already sorted. Why look at things again? So that's why you get the best case as order n. Worst case is obviously n squared. Now let's look at what is the case, or like how do we make sure that even my selection sort, which is like very greedy like, can I modify it somehow so that that also becomes or best case order n? Let's see. Let's take some random input, right? So I had 5, 3, 8, 4, 6. Now the way selection sort works is you go from the beginning, you look at this, you try to find the minimum element in the array. This is the approach just before bubble sort that I had talked about. You try to find out the minimum element in the array. In this case, I find 3 as the minimum element. And for this, I take an order n loop, right? In order n, I find minimum of the array. Now, if in this iteration only, I would have figured out that the array is sorted in this order n, if I figured out that the array is sorted, which is all of ai is less than ai plus 1, then my work is done. However, if it is not, then the smallest number that I found, which is 3, I try to swap it with the previous element. Basically, I try to put it here and shift all of the remaining numbers one step to the right, which means the array now becomes 3 here. I have 5, 8, 4, 6. In fact, let me just change the array a little bit so that it becomes slightly better. Imagine if the array was 4, 5, 6, 8. When I do the swap, then the array becomes, or when I push it here, then it becomes 3 comes to the beginning, and then I have 4, 5, 6, 8. Now, again, I know that at this point of time, 3 is at the right position. I still need to sort the remaining array. I'll again have to do an order of n minus 1 loop, this, and this to figure out the minimum number. In this case, it is 4 as the minimum number. But by the way, in this order n minus 1 loop, I figured out the array is already sorted. So I can therefore stop my process. The key thing to do here is when you find the minimum element, you don't just swap, but you shift the prefix of the array one step to the right, create space for this new element, and then you put it in the right place. If you do that, then the selection sort also becomes best case order n. One thing is, in most cases, you will neither be using BubbleSort or SelectionSort or InsertionSort. Actually, InsertionSort may be in certain cases, but most cases you will not be using these. These are algorithms that are good to think about. The approach that we utilized here, this might come into use later on in some or the other kind of context or in some or the other kind of problems. But the sorting algorithm that is currently in use in most of the libraries that you use are either merge sort or quick sort. Quicksort as being the most popular one because it has better average performance, does not use additional memory. But those are the ones because they sort of perform in order of n log n time. All of these are worst case order of n square. Average case is also order of n square almost. Java 8's array.sort also uses quicksort. But like BubbleSort, Insertion Sort, 3 algorithms that I talked about, they're good to know from their approach standpoint because there are some problems that might utilize this approach. These are not necessarily the sorting algorithms you'll use in day-to-day. Sorting algorithms that you will use, I'll talk about that in a few moments. But just so that I, again, complete my discussion on selection sort, let me write the pseudocode for selection sort. Pseudocode is very simple. Right now, if I have to sort, imagine when I is 0, I need to sort everything from 0 to n, right? So what I do is I take, this will go to some number, I'll figure out what. I'll take the loop from I to n. I'll figure out the minimum. In fact, let me actually also track its index. I can just keep it as a of I, and index is equal to I. And this loop can run from I plus 1. So if, let's say, a of j is less than min1, then minimum is equal to a of j, index is equal to j. Here, one of the other things which I also track is if a of j is greater than a of j plus 1, then there's a flag that I set to, let's say 1. Let's say there's a flag here which is also 0. And once I have found my minimum, then all I need to do is all of the other numbers, they are shifting one space to the right. So once I have found the minimum, I will take a loop of j is equal to, And then at the end, you have a of I is equal to min1. That is one way of shifting. Basically, what I'm doing is if I have an array, let's say I have 5, 6, 3, 2, 8. I'm going through once to figure out what is the minimum. Once I find the minimum, I bring minimum to the front, which is 2 comes here. And then 5, 6, 3, I shift one space to the right. And then I try only sorting this piece, where every single time I have a flag to check, is this piece already sorted or not? If at all at any point of time I find that there is a section of array that is already sorted, then I just break out and I'm done. Here, I mean, I could very well also have done, instead of doing all of this, I could have done swap a of I comma a of index. I could have done this as well. As long as I'm checking that for the remaining array, is the array sorted or not? If the array is sorted, then I just break. That is the only optimization that I put in, nothing else. Now I'm going to be covering a few other sorting algorithms, and then we'll do a few problems on these. CountSort is the easiest one. CountSort is when the elements that you are sorting, they are limited in range. Limited in range meaning, for example, I tell you, hey, you have characters A to Z. You have a lot of characters and you need to sort them. Or you only have numbers 0 and 1. Or you only have numbers from 1 to 20. Then what you do is, instead of counting or basically maintaining like numbers themselves, you just count how many numbers. For example, I gave you an array of zeros and ones, right? So bunch of 0, 1, 0, 1, 1, 1, 0, etc., etc. And I told you to sort this array. One very simple way would be I calculate the frequency of 0 and frequency of 1, which is basically exactly what CountSort means, right? Like you're maintaining the count of the numbers themselves. So you say like, I'll count how many times 0 came. Let's say 0 came 10 number of times. And I'll count how many number of times 1 came. Let's say it came 5 number of times. Then I know my sorted array. My sorted array is 0, 0, 0, 0, 0, 10 times. And then 1, 1, 1, 1, 1, 5 times. So one very common application of this is, if I give you two strings and I ask you, are these strings anagrams of each other? Anagrams is like two strings are anagrams if they are just some or the other permutation of the same string. For example, if I give you a string banana and I give you another string, let's say, this is not really a word, but I give you these two strings, right? And I ask you, are these anagrams of each other? Your answer will be yes, because they have the same count of n. There are two n's here, there are two n's here. They have same count of a. They have three a's here, there are three a's here. And they have same count of b. You know that you only have 26 different characters. So in a 26 array of size 26, you can maintain the counts of number of a's, number of b's, number of c's, and so forth. And you can just compare the counts, right? So CountSort is very simple. If you have limited number of numbers, if your range is very limited, you maintain the count of every single number you encounter, and then like you just print those numbers, those many number of times you go from start to beginning. So we are going to maintain a new array for 0 and 1. However, 0 and 1 are just two numbers, two variables. So it is still order 1 space. If you only have, let's say, 20 numbers, then it's just order of 20 space, which is not order n, right? Like it is not dependent on the number of numbers that you have in total. Let me maybe give you an example, right? And then I'll write code for it that will make it clearer. Very simple. Imagine I give you a string of characters, and I just ask you to sort that string of characters. For example, let's say the string is congratulations. Let's say that is the string. And then there were a bunch more characters as well. But like, let's just say that this is the thing. There could be, let's say, thousands and thousands of characters here, thousands, hundreds of thousands of characters. Now, one conventional way of sorting is like doing the bubble sort or the selection sort, etc. Right? Which is a selection sort would be you figure out which is the smallest character, which is A. You shift A to the front. However, I mean, if there are a lot of characters, that will take a lot of time. So what I say is, hey, by the way, I know that the kind of letters could only be from A to Z. Correct? I have A, B, C, D, E, F till Z. Correct? There are only 26 characters possible. 26 different characters possible. So if I somehow maintain the character count, right? I have only 26 characters. If I have an array which has the count of what are the number of A's here, what are the number of B's here, C here, and so forth. For example, when I encounter C, I say, let's increase the count of character C by 1. So C's count becomes 1. And I mean, this could be just be an array, right? Because any character can be mapped from a number from 0 to 26. So I just maintain an array of size 26. which is all initialized to 0 to begin with. When I encounter C, I increase the count of C by 1. Then encounter O, let's say O is somewhere here, I increase the count of O by 1. When I encounter N, I increase the count of N by 1. With R, I'll again increase the count of R by 1. A will become 1. Let's say when I encounter A again here, A's count will become 2. So that way, I mean, I'm just maintaining count of every character, right? Like, and if I have to write code for this, I would just do very simple. I would say that, you know what, like I have a array of size 26, which is initialized to 0. This is C++ format, but like Java, etc., it will be similar. And then I just say, you know what, like, let's assume that the character is CH, and I go over this string str, and I just say that ARR of CH minus A, which will now give me a number from 0 to 26 plus plus. At the end of it, I'll have frequency count of every character. And then like the sorting is very simple. I just go character by character, right? So I just go from for I is 0 to 26. I look at the count of the current character. Like for example, when I is 0, then I'm looking at the count of A. So what I do is I take a loop from 0 to ARR of I, whatever is the count. And I print A plus I, those many number of times. So what will happen is if the count of A was 2, then this will print A twice. Then let's say if the count of B was 1, then it will print B. If let's say the count of C was 3, then it will print C 3 times, and so forth. So all I'm doing is I'm just counting the numbers, frequency of the numbers, and then I'm just printing in them those many number of times, going in the order of numbers. Does that make some sense? CountSort, how is it working? As long as the range is limited. For example, let's say if you have numbers from minus 20 to 20, even then you can use the array, right? Because you can just say that every single number, num, corresponds to the index num plus 20. So when you encounter num, you just say, you know, ARR of num plus 20 plus plus. And when you print, then like for ARR of i's count, you print I minus 20. In general, if you see for doing this, if you have a range of numbers, let's say the range is R, CountSort takes order of R memory, right? If the range from min to max of the array, if the range max minus min, if this is R, then it takes you order of R memory, right? Because you need those many number of counts variable, right? If R is small-ish, for example, let's say if R is 1,000 or 10,000 or 100,000 or 1 million, if let's say R is up to 1 million, then you can use CountSort because you can maintain the counts and therefore like it will still run. However, let's say if the numbers were not limited, if there could be any integer, then you can't use CountSort. CountSort is only applicable when the numbers are limited in the range. As I showed with counting characters in a string, because characters are limited. Characters can only have 26 different values. So it is not done in place in the sense that you're still counting the number of A's, number of B's and C's, and then you can fill it in the same array. For example, if you said, tell me here instead of printing A plus I can just say, you know what? Let's have an index variable, which is 0. And I have, let's say my original string was str. I can just say, you know what? Str of index plus plus is equal to I plus A. I can fill it in the same array instead of printing, but I mean, you'll still have to maintain counts, etc. Merge sort is if imagine you had to sort a deck of cards. One possible way, which is, by the way, also called divide and conquer, could be that I break down this deck of card to half deck of card and half deck of card. So I divide into two parts, right? Like half goes, let's say, to the left, half goes to the right. I sort those individually, right? So half deck of cards, I sort them somehow by some magic. And right side also I sort somehow by some magic. So now I have two sorted deck of cards, right? I have two sorted deck of cards. Now the problem becomes, if I have two sorted deck of cards, can I merge them so that they still remain sorted? Imagine, let me give you an example, right? So let's say I have an array 2, 3, 5. Let's say I have another array 1, 6, 8. If I was given these two arrays, can I merge them into another array which is completely sorted? Is that possible or not? If that is possible, then this could become another algorithm, which is like whenever I need to sort an array, I can divide it into two parts, recursively sort them, and then I can merge them. So merge becomes the important step. The question is, I have given you a problem. You have two arrays. not necessarily of the same length. Let's say this is of size A, this is of size B. Can you create another array of size A plus B where all of the elements come from A or B and they're all sorted? Is the question clear? Like you have some A number of arrays in array A, you have B number of elements in array B. Array A and B are individually sorted. So A is a sorted array, B is also a sorted array. You have to merge them into another sorted array. How would you do that? Basically, if I have been given two numbers, let's say I have an array A, 2, 3, 5, and I have an array B, which is, let's say 1, 4, 8. And I have to create a sorted array, right? Which is of size 3 plus 3, which is 6. 1, 2, 3, 4, 5, 6, correct? This is the eventual sorted array I have to contain or create. One thing is the first element in the sorted array is going to be the completely minimum of everything in the array, right? So given array A is sorted, minimum from array A is on position number 0, correct? Minimum from array B is also on position number 0. So therefore, whichever is the minimum of these two, I don't need to look at any other element. Whichever is the minimum of these two is going to be the first element in the sorted array. Is that something you all agree with? And what is the minimum of these two? Minimum of these two is 1. So 1 comes here. Now, if I have inserted 1 here, then it is as good as saying that now I remove 1 from B. It is the same thing, right? So what I just do is, how do I remove 1 from B? I just change this pointer to now point at this number 4. This is as good as saying that I'm now merging two arrays, one array which is A and one array which is B, but B is starting from this point onwards. And I again do the same thing. What is the next number that should come here? It should be the minimum of numbers here and minimum of numbers here. What is the minimum of numbers here? Array at this pointer. What is the minimum of numbers here? The array at this pointer. Whichever is smaller, which is 2, comes here, and this pointer moves one step forward. So in short, the approach becomes that you have two pointers. Let's say there's a pointer 1, which is for array A. There's a pointer 2, which is for array B. And you just say the following: while pointer 1 is less than whatever is the size of A and pointer 2 is less than size of B, you do the following. You figure out which one is smaller. You just check. If A of pointer 1 is smaller than equal to B of pointer 2, then simple. This is what goes in the sorted array. So let's say sorted of, let's keep an index, A of pointer 1. You increment the pointer 1 plus plus because now pointer 1 has been assigned here. Else you put pointer 2 element here. So sorted of, again, index plus plus is equal to B, pointer 2 plus plus. The only thing is when I'm done with this while loop, it is possible that all of the smaller elements are in one of the array. Imagine like this array was 1, 2, 3 here, and there were, let's say, 4, 5, 6 here. My pointer 1 will end up going here, and I'll end up breaking out where I've only filled in 1, 2, 3 in the sorted array. 4, 5, 6 is yet to be filled. So I'll have to check for that, which is at the end of this while loop, if whichever pointer is not done. So I just check while pointer 1 is less than size A, I just keep adding sorted of index plus plus is equal to A of pointer 1 plus plus. And very similarly, I do the same thing with pointer 2. While pointer 2 is less than size of B, same thing, sorted B of pointer 2 plus plus. Right. That will cause the merge to happen. Does this make sense? Right. Now, if that can happen, which means now if merging can happen, and what is the time complexity of this merge? Imagine I have two arrays of size n and n each, n plus n, right? Like, so it takes me order n time to merge. If in fact the array A was of size m, this was of size n, it takes me order of n plus n time, right? That means if I have a order n array to be sorted, if I divide it into two parts, I say that sort the first part separately, sort the second part separately. Once they are sorted, then merging them will take me order of n by 2 plus n by 2 time, which is order n time. So merging them will take me order n time. Now, how do I sort the first half of the array? I can do the same thing with the first half as well. I can say that even to sort the first half, again break it down into two parts, and then sort the first half, sort the second half, merge it. with the end condition being that once I have an array of only size 1, it is already sorted. How about I modify this and I say that I have 3 arrays that need to be merged, right? Imagine I have an array 2, 5, 10. Imagine there's another array 1, 8, 9. And imagine there's another array 3, 4, 12. Let's say there were 3 arrays, right? How would you merge these 3 arrays into one array, which has all elements are sorted? We can do 2 at a time, but we don't necessarily need to, right? Like we look at this, right? What is the first element going to be in the merged array? It is the smallest of all. Where does the smallest come from? It is either the first element from here, or the first element from here, or the first element from here. Whichever is the minimum from here, that becomes your smallest. So I can have 3 pointers. Pointer 1 pointing to the 0th element, pointer 2 here, pointer 3 here. Whichever is the smallest of these 3, which in this case is 1 comes here. And then all I do is I move this pointer 1 step to the right. And I again repeat the same thing. Whichever is the smallest of these 3, which is 2 comes here. And then 2's pointer moves 1 step to the right. Now again, 5, 8, 3, whichever is the smallest, 3 is the smallest, 3 comes here. And 3's pointer moves to the right. 5, 8, 4, 4 is the smallest, so 4 comes here. And its pointer moves to the right. 5, 8, 12, 5 is the smallest, so 5 comes here. And 5's pointer moves to the right. And then so forth, right? In the case of merge sort, it is only 2 arrays. An extension of the previous question. Then instead of 2, if there were 3 arrays, how do you go about merging 3 arrays? I mean, you can merge 2 arrays at a time. You can merge these 2 at a time, and then you end up merging these 2. But you'll end up using more memory, because to merge these 2, you'll need an additional array of size 6. Then you'll create an array of size 9. What I'm doing is I'm just directly creating an array of size 9 so that I reduce the amount of memory required to maintain that intermediate re-array. Also, I reduce a step. Okay, all right. Coming back to the merge sort. How does merge sort work? As the name suggests, it's divide and conquer, which is basically, now that I know that I have the superpower of taking 2 sorted arrays and merging them, what I can do is given an array A, I sort the first half. So sort A to 0 to n by 2, sort A of n by 2 plus 1 to n, and then merge these guys. That can become my approach. And this, how do you sort the first half? This also can happen in the same way, where you again divide into 2 parts, 0 to n by 4, and then n by 4 to n by 2, and again, then you merge, etc., right? And if I have to write code for this, it becomes fairly simple, which is, let's say if the question was, how do you sort array A from index I to index j? If obviously like the size of the array is already 1, which means if j is equal to I, let's just put that, then your array is already sorted, so you can just directly return. If not, then what you do is you basically sort the first half, which is you say, I'll go from A of I to mid, where my mid is I plus j by 2. Then I'll sort A from mid plus 1 to j. And once these 2 guys are sorted, then I will need a temp array where I'll merge the array from I to mid and mid plus 1 to j. And then I'll make sure that A of I to j becomes equal to temp. I'll just do that. But basically, I'm just applying recursion here. And what I'm saying is, if you want me to solve, by the way, let's say there are 4 numbers, right? 5, 3, 2, 6. Let's say those were the 4 numbers. I say that first sort the first half. So let me call the function to solve these 2 numbers, 5 and 3. Somebody sort this and then give it to me. And then sort the second half separately. So somebody sort 2 and 6 and give it to me. And once I have them sorted, then I will actually merge them, right? Now to sort 5 and 3, I again do the same thing. I split it half. I say somebody sort 5 for me and somebody sort 3 for me. Here also, and somebody sort 2 for me and then 6 for me. Once they are sorted, then I'll merge. 5 is sorted, 3 is sorted. How do I merge? In my merge step, the same way we had seen, we have 2 arrays. We have to merge. When we merge, this will become 3, 5. And that is what I replace my original array with. So this array becomes 3 and 5. Very similarly, 2, 6 remains 2, 6. And then once I have 3, 5 and 2, 6, then I merge them to find 2 comes first, then comes 3, then comes 5, then comes 6. And this becomes my actual sorted array, which I replace this with. Just out of curiosity, why do we divide them into equal halves? Although in the end, we move two single elements and merge them in sorted order. Can't we take pairs in the array and do the same way of merging? Let's say I have more numbers, right? So imagine I had 5, 6, 8, 1, 2, 13, 15, 12, 3. How many do we have? We have 4. And let's imagine I remove 12 from here. Question is, if we have to sort anyway, why don't we take pairs by pairs, right? So let's just take pair 5, 6, 8, 1, 2, 13, 15, 3. And let's just first sort them. So we end up sorting them. And for example, we end up finding that this is 5, 6. This becomes 1, 8. This is 2, 13. And this becomes 3, 15. Right. Now, the problem is like we've done pairwise sorting, but the array is still not sorted. Then we'll have to do sorting of 4 elements each, right? How do we do that? We say that, you know what, like there are first 4 elements here. The first half is sorted. The second half is also sorted. Let's merge somehow, which again, I'll take another array and then I'll merge, etc. So this will get sorted. Then I'll do again the same thing, which is I take 4 elements, half is sorted, and I'll do the same thing. And then finally, I'll look at all of the 8 elements. So you're going just in the reverse order. What I just said, you're just going in the reverse order, which is also correct. It's just harder to code because the previous approach can be coded using recursion, which I'll just show. In your approach, what you're doing is you're building bottom up, right? Like you're sort of saying that let's first sort all pair of elements. Once they are sorted, then let's look at all 4 size elements. Great. Once they are done, then let's look at all 8 size chunks. Once they are done, then look at all 16 size chunks, and then 32 size, and then 64 and so forth. Right? And finally, I'll have the entire array sorted, which works. It's just harder to code. What I said was the other way around, that instead of going from 1 to 2 to 4 to 8 and so forth, let's start from n. Let's divide that into n by 2 parts, then n by 4, then n by 8. And I'll finally reach the 1 part anyway. And then my recursion function will keep returning and I'll have the eventual answer. So if you look here, my recursive function, this will do the same thing. My recursive function here will also do the same thing. Let me also just write it as merge step. So what is happening is, if I have an n-sized array, I'm dividing it into 2 arrays of size n by 2 each, n by 2 each. I'm sorting it using the same methodology, which is this n by 2 will create arrays of size n by 4, n by 4. Here also, again, same, n by 4, n by 4. These will create arrays of size n by 8, n by 8, again, n by 8, n by 8, same thing. And this n by 16, n by 16, and so forth. How many levels will you have here? I mean, we go from n to n by 2, n by 2 to n by 4, n by 8, 4 to n by 8, n by 8 to n by 16. How many levels? Log n levels, right? So in every level, n is becoming half of what it was. As we have seen the same pattern in binary search, etc., etc. I mean, as you go, if n is becoming half of what it was, it takes you log n steps to finally come to 1. At every step, what is happening? At every step, basically, I have n by 2 sorted array. I'm merging them, which takes me order n time. This takes me order n time. N by 2 plus n by 2 and order n. What happens on this level? These 2 guys merge and it takes them n by 4 plus n by 4, which is n by 2 time. These 2 guys merge and it takes them n by 2 times. If you add them up, it will take you order n time on this level as well. Very similarly, on the other level as well, where you have n by 8, there are 8 instances of n by 8. It will again take you order n time. So the total time taken on every level, it takes you order n time. There are log n levels. The total time taken is n log n. That is an intuitive way to understand. I can also explain the mathematical way of explaining this. But the intuitive way of understanding the time complexity of merge sort is that on every level, you're doing one merge. The merge is order n. Number of levels is log n. And therefore, in fact, if you look at Arvind's approach, if you were to implement it, in every iteration, what you're doing is you're first creating pairs and you're merging the pairs. Takes you order n time. Then you're looking at all 4 blocks, right? Like blocks of 4 each. In one order n operation, you will have sorted blocks of 4 each. Then in again one order n operation, you would have sorted blocks of 8 each. And you'll keep doing that till you cover the entire array. So the number of steps to cover the entire array would be log n. And every single iteration is an order n iteration. So it takes you an order of n log n. I can explain the math behind it as well. Is it n log n in every case? Best case is, sure, I mean, you can probably put an optimization there that if the array is already sorted, if a half is already sorted, you don't need to do all of the splitting, etc. So best case, you can still make order n. But yes, worst case is order n log n. Worst case, it takes you order n log n. And you can put a check to make sure that you're not doing the entire splitting, etc. if the array is already sorted. All right. What is the space complexity of merge sort? So if you look at the implementation here, we are allocating this additional memory temp to calculate this merged part, right? Why? Because when we are merging two sorted arrays, we need this temporary space where we put in the result, which is not a part of the original array. This is additional space. If I have to look at this tree, in this n by 2 part, I would have taken a temp array, which was of size n by 2. Here, I would have taken a temp array, which was of size n by 2. In fact, let's look at total space allocation, right? So this n by 2 will make a call to n by 4, 8, etc., etc. So this is a log n stack memory space. Plus, in each of these, so imagine I was sorting this array of size n. This will end up calling for n by 2. This will end up calling for n by 4, n by 8, and so forth. In each of this, I would have a temp array allocated, which will be freed as long as, I fill it back, right? So this temp array here is of size n by 4. As soon as I am done, then this will be freed. Then I come back here. Here it will be of size, additional size of n by 2. As soon as I'm done, it will be freed. And then I'll come back here and I'll have a temp array additional size n. So maximum space that I end up using additional is I have log n stack of recursion, plus I have this additional order n size array that I might have used, which is my temp array. So order n extra space is what we end up using apart from the array space. So space complexity becomes order n. Time complexity becomes order of n log n. There's one more way to, by the way, calculate time complexity. If you assume that the time taken for sorting an array of size n is tn, then tn is nothing but, I'm saying first sort array, first half of the array, then sort second half of the array, which is also of size n by 2, and then merge them, which is it takes you some n time. Let's say it takes you n time. This is basically saying 2 times t n by 2 plus n, right? If you break it down further, your n by 2 is 2 times t n by 4 plus n by 2, which is the same as 4 times t n by 4 plus 2n, which you'll see will finally come to 2 to the power I t times n by 2 to the power I plus n into I. This is just a little mathematical. Therefore, I explain the intuitive way first, which if you want this to become equal to 1, I becomes log n. So you have n into t times 1 plus n into log n, which is n log n. This is how Master's theorem actually works. I'm just elaborating that, expanding that equation. Even if you don't know about Master's theorem, that is fine, as long as you understand the intuition of why it is n log n. Because in the recursion tree, there are log n levels. On every level, I'm using order n time. So time complexity becomes order of n log n. Space complexity becomes order of n. Is there any way without using the extra space? So actually merging two sorted arrays without using extra space in order n is not possible. That becomes the blocker, right? So if you can merge the array in place without using extra memory, then your problem would have been sorted. But the problem is merging without extra memory is the issue. All right, does this make sense? Merge, sort, space complexity, time complexity, all of that. All right. Today we'll be talking about quick sort, and today we'll be solving a lot more problems actually. By the way, I just wanted to maybe also share one news with all of you. Today was the first case when one of the fellow students at Scalar has gotten an offer as a CTO at one of the energy companies, which is a fairly big company now, right? And that the reason why I'm sharing this with all of you is to show you that, look, learning matters. And again, I can't disclose the exact salary of the person, but it is in a few CRs. We're not talking about lakhs, right? So the thing that matters at the end of, that is basically the North Star for all of us. He's 30 something, but we all should focus on the learning aspect. As long as we do that, eventually all of us will succeed. We'll go and build really, really great things in the future. He is part of Scalar Academy and not Scalar Plus. And I can't disclose the name of the company. And I'm sure like that news will come out later on. It will be shared with all of the community as well. Once he joins, it's still sort of confidential. But just letting you guys know, I mean, look, it is important that all of us focus on learning. As long as we do that, I mean, obviously, like what you find later on is going to be a function of what you know at present, plus like some bit of experience. I mean, so again, just to also elaborate, this person is not somebody who is very young. As I said, like he's 30 plus, already has more than 7-8 years of experience, actually has more than 10 years of experience. But as long as you keep learning the right things, you'll keep moving forward, right? And that is, all of us should just aspire to become 1% better every day. That being said, back to what is the agenda for today. Today, we're going to actually talk about one sorting algorithm, which is actually used in most libraries that you use, be it in Java or Python or C++. The sort function that you use, they all use a different algorithm, which we will talk about today. But instead of talking about the algorithm, which is, I believe, not the right way to introduce a concept, what I'm going to do is I'm going to give you a problem, a real life problem that you may take an attempt at solving. And then we'll use that to maybe introduce the approach. So imagine this. Imagine you have a bunch of nuts and bolts. You have nuts and bolt, right? So nuts basically look something like this. And then you have bolt that is basically a circle that fits into the nut. The nuts and bolt, and usually like they're created in pairs, right? So you have a nut of a size and then the bolt actually clearly fits. If the nut and bolt are of the same size, then they fit. Now imagine you have a lot of nuts and lots of bolts. And you are given that every single nut is of unique size. It is every single nut and bolt are of different sizes. So none of them have the same size. And you're also given that every nut has a corresponding bolt. One fact that is given is every nut has corresponding bolt, which means they both fit each other. 2 is no two nuts have same size. So they're all different sizes. However, it is very hard for you to just visually differentiate which one is bigger or which one is smaller. So what do you do? What you do is, like, if you pick a nut and you pick 2 bolts, if the bolt is loose, then you know that the bolt is bigger. If the bolt is not going in, then you know that the bolt is actually smaller. Now the problem is, given that info, can you sort all of the nuts and bolts in increasing order of their size with the right nut and bolt paired up? Currently, they are all just in this array. You have a table full of nuts and bolts. You don't know which one is paired up with which one, right? One is how can you arrange that? And 2 is how can you do it as fast as possible? Let me explain again, right? So imagine this. Let's say I had only 2 nuts. Imagine I had this nut, another nut, and I had another bolt and then another bolt, right? Now, what I can do is I can pick, let's say, this particular one, and I pick this one, and let's say I try to match them. There are following things that can happen. One is these guys clearly fit. In that case, I know that this nut is to be paired with, let's just call it bolt 1, bolt 2. This is nut 1, nut 2. If they fit, then I know these guys are in the pair. They belong together. And then I can just compare the other bolt. If it is smaller than this particular nut, then it goes before this nut, right? If it is smaller, otherwise if it is bigger, it goes after. And then I definitely know that the pair for this bolt is this nut, right? So I just put these 2 guys together, either after or before, depending on how it compares with this current nut. So if I have to define the problem formally, you can pick a random nut, an X, and you can pick a random bolt. If you pick these 2 guys, you will get either of the following result. Either you will get nx is equal to by, which means both of these guys belong together, or you will get to know that, by the way, this nut is smaller than bolt, or you will get to know that nut is bigger than bolt. These are the 3 results you can get. You cannot compare nut with nut. So for example, I cannot get nx and ny and compare these guys. I can't. Similarly, I can't compare bolt with bolt. This I can't do. This I can't do. However, I can take a random nut and a random bolt and I can compare them. Does that make sense now? It does, right? Now, I mean, the question is, how do I sort these guys? How do I sort these guys? When I can't really compare a nut with a nut and a bolt with a bolt. The bolt size is not given to you. I mean, think of it like this, right? You have a table which is full of these nuts and bolts, and there's only minor variation in the size. What you should end up with, for example, in this case, imagine that these guys were equal. N1 and B2 was equal. So I would put N1 and B2 together and assume that B1 was smaller than N1. So I would put N2 and B1 before this. And I will return this list. N2, B1 as the first entry, N1, B2 as the second entry, right? So if you just compare with a bolt with a nut, you do get the relation whether a nut is bigger than a bolt or not. So imagine if this nut was paired with another bolt, BZ, then you know that BZ is actually smaller than BY. So you can compare the pairs by picking nut from one pair, bolt from another pair. There is no size given. The only way is you just pick a random nut and bolt and then compare whether one is smaller than the other or not. Let's actually look at how do we do that, right? So one is, if I pick any random nut, let's say if you're given, let's say n different nuts, let's say I pick some random nut. Let's call that nut N1, right? What I can do is now I have a bunch of bolts. I have B1, B2, B3, B4, B5 till Bn. I can compare each of those bolts with this N1. And I'll basically get three kinds of bolts. There will be one heap of bolts which are lesser, right? So there's one heap of bolts which are smaller than N1. There is one heap of bolt that we will get. Let's call this bolt bigger, which is bigger than N1. And there is exactly one bolt that I will get, which will be equal to this nut, correct? If I compare all of the bolts with this nut, I'll get three sets, one bolt which is equal, and then a set of bolts that are smaller and set of bolts that are bigger. How these guys compare amongst each other, that I don't know. But essentially, I do know which bolts are smaller than this nut, which bolts are bigger than this nut. That you guys all agree with? So if I pick any random nut, I can distribute all of these bolts this way. And very similarly, now that I know that this bolt is the same as this nut, so I can pick all of the nuts, which were N2, N3, N4, N5, N6, N7, N8 till N. And I can say, let me compare all of these nuts with this bolt, right? I'll get some nuts that are smaller. So I'll basically have some of these guys. If I compare with this bolt, I'll get some nuts here. Let me take a different color. Some nuts here, which are smaller. Some nuts, which are bigger. The equal one is already here. So you'll not find anybody who's equal. So what we have done is we first started with one nut, right? And then we use that to break all of the bolts in three parts. One bolt which is equal, a lot of bolts that are smaller, a lot of bolts that are bigger. And then once we found the equal bolt, we use that bolt to actually split the nuts, remaining nuts, into two parts, smaller nuts and bigger nuts. Now what I know is all of the bolts, smaller bolts, will have their corresponding nut somewhere here. Basically now I have three sets, right? I have a set of nuts and bolt which are smaller. And they are guaranteed to be present in pairs here. Same guarantees holds here. Then I have one pair which is N1, B1. And then I have set of nuts and bolt that are bigger. Now I can actually recursively sort this set separately, and I can sort this set separately. But my problem has now reduced to sorting smaller set of nuts and bolts. And if the set only had one element, then I know that they are already sorted. I don't need to touch them. This is exactly how QuickSort works. I'll introduce it very, very shortly. But let me take a few examples just to show how is this working. And that will give you a sense of or sort of some intuition behind how QuickSort works. So imagine I was given some random, let's say N1, N2, N3, N4, N5 nuts. And let's say I had random 5 bolts as well. What I'm going to do is I'm going to mark, let's say hypothetically, what the process is going to be like. So what I'll do is in step 1, I'll pick this nut and I'll say, let's compare it with all of these 5 bolts. And we'll find some bolts that are bigger, some bolts that are equal. Imagine, hypothetically, let's say N1 was equal to B3. And imagine that B2 and B4 were smaller bolts. And we found out, let's say that B1 and B5 are bigger bolts. Very similarly, then what I did was that I picked B3 and I started comparing B3 with all of these guys, N2, N3, N4, and N5. And I would come to know whether they are bigger than B3 or smaller than B3. All of the bolts, again, let's say hypothetically N2 and N3 were smaller, and let's say N4 and N5 were bigger. Now the problem becomes that I know that N1, B3, whenever I sort, is going to be the third element in the set. I have 2 elements before. I don't know their order, but those 2 elements have basically B2, B4, N2, N4 as 2 pairs. And I have two elements after, which is B1, B5, N4, N5 that are yet to be sorted. That is after, right? However, this portion is fixed. I don't need to change this portion. It is in the right position. It is where it should be. I do not need to change this position. This is already in its correct position. So then what I do is I recursively sort the first half. And then once this is sorted, then I'll go to the second half. How do I sort the first half? I again do the same thing. I say, let's pick a random nut. Let's say I pick N2 as the random nut. And I compare B2 and B4 with it. Oh, sorry, this should be N3. So B2, B4, N2, N3, B1, B5, N4, N5. Right. Okay. So then let's say pick N2 as the one nut, right? And I compare B2 and B4 with it. I know that I don't need to compare B1 and B5. They're definitely bigger. I'll deal with them separately. I'm only concerned with sorting these two pairs. So I compare B2 and B4. And hypothetically, let's say I find that N2 is the same as B4. So I find these guys are equal. And hypothetically, let's say I find that B2 was bigger. I know that B2 will be paired up with N3. So I put it as it is. These guys are sorted now. Then I have N1, B3. And I do a very similar process here as well. I pick any one of these guys. Let's say I pick N4. And hypothetically, let's say N4 pairs up with B1. And I find that B5 is smaller. So therefore, B5 will come here. The pair of B5 is N5. That will come here. So this becomes your sorted array totally. Now this process where I actually picked one element and I started comparing all of the remaining elements with it is called choosing a pivot. So while this is a more complicated case, let me take an example of sorting an array of integers. And I'll show you with that. Imagine, let's say my array was 5, 2, 1, 8, 6. N1 or B3 is largest. That means this set does not exist. The set is empty. But the remaining set is still smaller set than what you began with. It has now n-1 bolt and n-1 nuts. So you still have a smaller problem to solve. So in every step, you're reducing the size of the problem. So that is actually your worst case where you will end up taking n square time. But still, I mean, that still gets you to your answer. So at each step, one of the pair comes at its right place. Let me just elaborate that with this array as well. So in the quicksort process, what you do is you pick one element, any random element, to be the pivot. For example, I say that I want to pick 5 as the pivot. So what you do is, the first part is you count how many numbers are smaller than 5, right? So you basically, let's say, have 2 is smaller, 1 is smaller, 8 and 6 are not smaller. That means the right position of 5 is the third position because there are 2 numbers smaller. So what you do is you put 5 here. 1 probably comes here. So your array is basically 1, 2, 5, 8, 6. And then once you have put 5 in the right position, then you compare all of the remaining elements. What you want is all of the smaller elements are on the left side, all of the bigger elements are on the right side, which in this case has automatically happened. But in case it wasn't, what you would do is you would start from here and you would start another pointer from here. The first number that you find on the right side, which is actually smaller than 5, you'll stop there. You'll try to find the first number from on the left side, which is actually bigger than 5. You'll stop there and then you swap those two guys. So in order n, you'll be able to get to a place where all smaller numbers are on the left side, all bigger numbers are on the right side. And then the problem becomes that 5 is in the right position. Now, as long as I can sort the left side of the array and right side of the array separately, my entire array will be sorted. And that I can again do recursively. So in every step, when I choose a pivot, one number will come at the right position and it will divide the remaining array into 2 parts, 2 smaller subsets that need to be sorted. Do we have to take pivot as the middle to make the swap easier? I mean, so if the thing is when you're choosing the pivot, you don't know which one is the middle element. I mean, you basically start with choosing a random number as the pivot in the array that you have to sort. If you are unlucky, then it would turn out to be one of the numbers, which is either the highest number in the array or the smallest number in the array. If you are, I mean, if it is just very, very random, chances are you'll find a pivot somewhere towards the middle. I mean, let me actually go step by step. Does the nuts and bolt approach make some sense? Basically picking one nut, comparing all of the bolts with it to divide them into smaller heap, bigger heap, equal to, and using the equal to bolt to divide the remaining nuts into a smaller heap, bigger heap, equal to. And I know that the equal to part is in the right position. Now I need to sort the smaller heap of nuts and bolts separately, bigger heap of nuts and bolts separately. Let me take another example of this. Actually, here there wasn't swap. Let's see what kind of thing we can do where we would need a swap. Imagine I still have 5 as the first element. Let's say there is 6, 8, 1, and 2. Hypothetically, let's say this was the array. And again, we chose 5 to be the pivot. If 5 is the pivot, the first step, let's count the number of numbers smaller than 5, 1 and 2. So that means 5 should come at position number 3 in the array. So 5 should come here. So what do? The quickest way is I just swap, right? So I just bring 5 here, I bring back 8 here. So 5 comes here, 8 comes here, I remove the circle. Now I know 5 is the pivot. What I want is all smaller numbers should be on the left, all bigger numbers should be on the right. Right now it is the opposite. So what do? I say that I'll start with a pointer on the left side. Let's call it start pointer. I'll also start with a pointer on the right side. Let's call it the end pointer. Or maybe we can just call it left and right. Both are also okay. Left and right. I compare the first number and I see whether it is in the right half or not, in the correct half or not, right? So 2 is smaller than 5. It should have been in the left half. So it is not in the correct half. So I make my right pointer wait here. My right pointer is currently pointing at 2. Very similarly, I start a loop on left to find the first number which is not in the correct half. In this case, the first number that I find, which is 8, is not in the correct half because 8 is bigger than 5. It should have been on the right half. And then the first place wherever left and right is, I just swap them. So essentially 2 comes here, 8 comes here, and I now know that these two guys are in the right half. So then I again start moving my left till I find the next number which is not in the right half, which is 6. So my left will wait at 6. Very similarly, I start moving right to find the next number which is not in the right half, which would be 1, and I'll just wait at 1. And I end up swapping 1 and 6. So 1 comes here, 6 comes here. So your right pointer will move from this position to this position, and your left pointer will move from this position to this position. If you add these guys up, you'll get total sum as n minus 1, n being the size of the array. This will help you shift all smaller elements to the left of the array, bigger elements to the right of the array. So if I have to write the steps of quicksort, one is choose any number randomly as pivot. And then once you have chosen a pivot, put pivot in the right position. For calculating the right position, you'll have to count numbers smaller than pivot. So this is one order n iteration. Third thing that you do is using left and right pointer, shift smaller numbers in left half, bigger numbers in right. So the fourth step is sort left part and right part separately. Can be optimized by choosing the correct pivot. The most optimal pivot is your median, basically a number which can divide the array into 2 equal parts. That is the best pivot, right? Because then you're left with smaller arrays to sort. It is obviously faster to sort smaller arrays. However, the problem is it is very hard to know what is the median of the array. Why would you want to spend a lot of time finding out the median? So what quicksort says is, as long as your pivot choice is completely random, if it is completely random, then you're still fine. Average time complexity will still become n log n. All right. What is the approach behind quicksort? Quicksort is essentially choose a pivot, divide the array into smaller numbers, bigger numbers, sort the smaller number separately, sort the bigger number separately. Your array will automatically be sorted. Divide and conquer. Most of the library functions that you use, they use quicksort and they choose pivot randomly. I'll explain why randomly still works here. The one thing which you will notice is in this entire process, we have not used any additional memory. We did the swapping, etc. in place. So we have not created a duplicate array. All of this is happening inside the same array. That is important because while merge sort also is order of n log n, which we will see with quicksort, merge sort uses additional space, or it requires this separate array where you merge the two arrays, which is additional memory required. So one of the reasons why merge sort is not used extensively, but quicksort is used extensively, is because quicksort does not use additional space. The worst case of quicksort is still really bad. Collections, you also use quicksort. Now, since we don't have random access, how does it work? For example, if you use what you're saying is, let's say if you've implemented the list with a linked list, then how would the quicksort sort of work there? Because here, if you see in the quicksort, you're not really doing random access. All of your access is still sequential, right? For example, let us go step by step. We say let's choose any number randomly as pivot. I can take a loop till the number because I'll still anyhow have to take an order n loop throughout the entire list to count the number of numbers smaller so that I know what is the right position. I'll have to do that anyway. So I take a linear loop to get to the number. That's fine. I take a linear loop to find out the right position. And again, I do the same thing. I anyhow have to split the numbers into left and right pointer. I can take a linear loop for that. So in all of this case, if you see, I'm not doing any random access. I'm actually going step by step in a linear loop. Let's do what is the time complexity analysis. Let's do what is best case, what is worst case, and what is average case. What is the best case with quicksort? What is the best pivot you can choose? Assuming that the array is not already sorted, what is the best pivot you can choose? Median. Let's say you were very lucky and you were choosing the middle element all of the time. What would happen is if you were given an array of size n, you would put the median in the right place. So median would be in the right place. And then you'll have an n by 2 size array here, n by 2 size array here. You'll need to sort these separately. So what happens is exactly like merge sort. You start with an array of size n. This reduces to sorting array of size n by 2 twice. One on the left side, one on the right side. That becomes, basically time to sort an array of size n is the same as 2 times tn by 2 plus order of n for merging. And this basically comes to order of n log n. So if you are choosing the median as the pivot all of the time, then you end up sorting it in order of n log n. If you are choosing the median as the pivot every time. And by the way, this is probably not the best case. Best case is when the array is already sorted. Best case meaning that if you're given an array and then your median is the best, right? So you end up sorting in order of n log n. What is the worst case? What is the worst kind of pivot you can choose? One end, when your pivot is actually on one of the ends. So what happens is in one step, in order of n, what you would do is you'll end up choosing a pivot that is on one end. So your pivot is here and you'll find all of the other remaining n minus 1 elements are on one side, which means that in one order n loop, you have only fixed the position of one element and you still have n minus 1 numbers to be sorted. And if you keep doing that again and again, if you're extremely unlucky, your time to sort will become n plus n minus 1 plus n minus 2 plus n minus 3 plus n minus 4, which is order of n square. So your worst case becomes order of n square. If you are very, very unlucky that you're choosing the extremes as your median all of the time. Does this make sense? Why is the best case order of n log n? Why is the worst case order of n square? Just in terms of how we choose the pivot. If we are really, really good with choosing the pivot, then we end up choosing the median as the pivot. That means it divides the array into 2 equal halves, which is exactly the kind of thing that we did in merge sort, right? Like you start with an array of size n, you end up with 2 equal halves of size n by 2 each, which you have to sort, which again will split further into n by 4 if you again choose median. This tree will have log n number of levels. On every level, you're doing order n operation. So your becomes the best case. If you're choosing the best pivot, then it becomes n into log n. If you are choosing the median as the pivot, then you'll have order of n log n complexity. That is clear to everybody, right? Okay. What is the worst case? Worst case is when you're choosing one of the pivot. Your time to solve or sort n sized array is in order n, you were able to fix the position of one element. The other n minus 1 still need to be sorted. And if I just expand on what tn minus 1 would look like, it would be n minus 1 plus tn minus 2, which is what? N plus n minus 1 plus, what is tn minus 2? N minus 2 plus tn minus 3, which if you keep adding up will become n square. I was not talking about the best case really. I was talking about given an array. If let's say I had flexibility on what I choose as the median. So what kind of pivot? What kind of pivot will give me the best complexity? What kind of pivot will give me the worst complexity? That was what I was looking at. Right. So what is the average case complexity? One algorithm that I wanted to address, which is called bucket sort. If you guys remember, we did something called a count sort, right? Which is when the elements were in limited range. We would just count the frequency of elements and that would help us sort. Bucket sort is a slight variant of that. Variant being that if I can categorize numbers into buckets where I know the buckets are sorted in some fashion, then the sorting problem becomes easier for me. Radix sort is exactly bucket sort. For example, hypothetically, let's say you had a lot of numbers. So let's say I had 456, 923, let's say I had 150, let's say I had 268, and let's say I had 12. And maybe I also have 950. Now imagine I was to create 10 buckets. Bucket 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Which is for the most significant digit of the number. Let's say the 100th place. of the number. I'm assuming that a lot of the numbers are smaller than 1000. They can be 1 million, 10 million as well. So then we'll choose the most significant bit and we'll keep it the same position for all numbers. If I do that, then I know that 423 will go in the fourth bucket. Most significant digit is 4. Most significant digit here, assuming for all of them, the most significant digit that we're looking at is the third digit from the back. So 923 will go in the 9 bucket. 150 will go in the 1 bucket. 268 will go in the 2 bucket. 012 will go in 0 bucket. 950 will go in the 9 bucket. What I know is, now if I start going bucket by bucket and I have sorted the numbers within a bucket, if I have sorted the numbers within a bucket, and if I just start picking numbers from here and appending them, then I end up getting the entire array sorted. Why? Because I definitely know that any number that is starting with 0 is definitely going to be smaller than any number starting with 1. So dividing them into buckets and then sorting the buckets within themselves, sorting the numbers within a single bucket, that helps me reduce the complexity to some extent. And I'll show you an example of that to a major degree, which is what is called as radix sort. But the idea is, if I can break them into buckets where buckets already have some ordering defined, then my job becomes just simply appending the numbers in the buckets, and that might give me a sorted array. And I'll give you a few examples to sort of talk about what bucket sorting is. And we'll do one problem on bucket sorting as well, which is a hard problem, but we'll do that. What kind of data structure can I use for buckets? Think of them as, for example, vector of int. So for example, your v of 0 is a vector of numbers. V of 1 is also a vector of numbers, and then so forth. So the concept of bucket sort is very simple. If you can split numbers into buckets, where buckets themselves are ordered in some fashion, then I can sort numbers within the buckets, and then I merge them. That gives me a sorted answer. If numbers are not on the same order, how do we put them in bucket? So even here, if you see, like 12 was not of the same order. I just added another 0 to get it to the same order. So imagine I have numbers as 950, 1, 12, 923, 256. I'll just add 0 to make sure they're all of same length. How do we keep the value sorted in one bucket? Within the bucket, just use quick sort or whatever kind of sorting you want to use there. Insertion sort, quick sort, whatever you want to use. Let's take an example. Bucket sort alone isn't enough. Bucket sort paired up with a few observations is actually very powerful. So one observation that leads to sorting algorithm is called radix sort. The way radix sort works, imagine again you have a bunch of numbers to sort, right? Again, I'll pick the same thing, which is, let's say I have 923, 950. Let's say I have 12. Let's say I have the number 1. Let's say I have number 100. Let's say I have 150. Let's say I have 650 and 688. Hypothetically, let's say I have a bunch of these numbers. So what radix sort says is, look, at the end, if I was at the end, let's make all of these guys equal length. So add zeros wherever applicable. If all of these numbers are of equal length, then at the end, most significant bit, this bit, is the most important bit. Obviously, if the most significant bit of one number is smaller than the other number, then the overall number is definitely smaller. It is only a problem when they both are equal. Then I will look at other digits. So I know that. So what I want to do is, I want to start sorting digit by digit, with most significant digit being the last place where I sort, because I know this is the final step. So what radix sort does is, it says, let's start with the least significant digit. Let's first sort based on this. And what do? I basically create, again, 10 buckets corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. I will first look at the last digit. Based on that, 923 goes here, 950 goes to 0, 012 goes to 2, 001 goes here, 100 goes to 0, 150 goes to 0, 650 also goes to 0, 688 goes here. And then I append these guys, right? What will happen once I have done this step? All of the numbers will be sorted by their last digit. So I get 950, 100, 150, 650, 001, 012, 923, and 688. I sorted numbers based on their last digit. Now let's look at the next digit. I repeat the same process again, but with the next digit now. I'm going to erase all of these guys from here. We are now going to look at the second digit. I say that now let's look at these numbers again, one by one. But the second digit is what we are looking at. So 950 goes at 5. 100 goes at 0. 150 goes again at 5. 650 also goes at 5. 001 goes at 0. 012 goes at 1. 923 goes to 2. And 688 goes to 8. I'll again append these guys. What this would make sure is now everything is sorted based on the last two digits. So I append, and when I append, I basically get 100, 001, 012, 923, 950, 150, 650, and 688. And now the last step is the magic step, which is where I look at the most significant bit. So I erase all of this again. I look at the most significant bit and I bucketize these guys based on the most significant bit. So 100 comes here, 001 comes here, 012 comes here, 923, 950, 150, 650, and 688. Now once I append them, all of the numbers should be sorted, which you would see 001, 012, 100, 150, 650, 688, 923, 950. Now this final array that we've gotten, this is sorted. What has happened? We can take MSB directly. The only problem is then within the bucket, if you have multiple numbers, and think of like when you have a million numbers, right? You only have 10 buckets based on MSB. That means every bucket on average will have 100,000 numbers. And if you go to solve or sort of sort each of those buckets separately, it will take you a lot of time. But here, I can sort the entire array by doing this function, the number of digits number of times. So imagine all of the numbers had 5 digits. I'll do this operation 5 number of times and my entire array would be sorted. For every single digit, I am putting them in buckets, 10 buckets, and then I'm appending them, which is an order n operation, right? So my total amount of time taken is order n into max number of digits. Space is assuming that we are taking a vector of vector. The total space taken by vector of vector combined across all of this is order of n. So I'm using an order on n extra space. Actually, order of 10 plus n, which is order n. Do we need to compare an element with the existing elements present in the bucket? No. Right now, because the moment you start doing that, then your complexity increases. Currently, it is just very dumb way of appending to existing numbers in the bucket. Why can't we take MSB to LSB? I mean, when we start with MSB, in the first step, we would definitely have put the bigger numbers to the first half of the array, the smaller numbers to the second half of the array. That I completely agree with. In fact, numbers would be sorted based on their first digit. But as you go to the second digit, within these numbers, if the sorting is happening in the right way or not, because you'll have, let's say you look at second digit as 0, right? Now, some of those 0 numbers will come from the numbers that had the first digit as 9. Some of those 0 numbers will come with some numbers where the first digit was 6. For example, let's look at this example itself, right? If I started from MSB, then what would have happened? Let me erase this. My first 2 numbers will go in the 9 bucket, 923, 950, 012, 001, 100, 150, 650, and 688, which is great. Now, if I append them, then I get this, which is almost sorted. The problem is when I move to the next digit, it's then that it becomes a problem, because 012 will come here, 001 will come here. Now 100 will also come here. However, I know that 100 should only come after 012. When I will merge, then I wouldn't know how to maintain this ordering. I mean, I'm using digits here. You can do the same thing for bits. There you will only have 2 buckets, 0 and 1. Here I have 10 buckets. You'll only have 2 buckets when you're dealing with bits. When you go from LSB to MSB, that means MSB takes higher priority because it is the last deciding factor. When you go from MSB to LSB, then LSB starts taking higher priority. So time complexity is n into number of digits. If d is the number of digits, that is your time complexity. Usually, the number of digits is the same order as log n. It's actually log n to the base 10. N being the maximum number in the array. Number in array. So, I mean, usually radix sort is good number to know and good approach to know because this can be applied at multiple places. That being said, again, like not very commonly used because n log n, you can just directly use your sort function. Why would you go and take the pain of implementing radix sort when it has very similar time complexity? If all of what we have discussed till now, if that makes sense, I'll give you one problem which will actually make the bucket sort even clearer. The reason why we have bucket sort. Explain the time complexity again. So if you look here, what are we doing? We are taking digit by digit, right? So first we look at the last digit. And for that digit, what do? We put them in these 10 buckets, right? So basically what happens is, what is the last digit of any number? Let's say I do this, right? I say I goes from 0 to n, and we calculate the last digit. Digit is equal to array of I mod 10. That is your last digit. And then you put it in the same bucket. So for example, let's say if you have bucket array, you say bucket of digit dot add AI, right? You do that. All of this is order n process for the last digit, correct? And then eventually I'll basically look at numbers in every bucket and I'll keep appending them in another array. All of this is order n process. I'll have to do this for every digit, correct? So if all numbers have, let's say, 5 digits, then my complexity would be n into 5, because for every digit I'll do an order n operation. If every number has d digit, then it becomes order of n into d. How n log n is similar to n into d. So n into d makes sense, right? Order of the algorithm is n into d. That makes sense. Correct. Okay. Now what is d? What is given a number x, what is the number of digits that x would have? How do you find that? Basically, how do you find number of digits? You basically divide x by 10. You check if it is 0 yet. Then you again divide it by 10 further, which is 10 power 2. Then you divide x by 10 power 3, x by 10 power 4, 10 power 5, and so forth, right? When x by 10 to the power I is 0, which is like now 10 power I has become bigger, then that is where you have the number of digits, okay? If I just put it like this, I mean, basically, if x has I digits, then x is approximately equal to 10 raised per I. Approximately, which means if I take log 10 on both sides, then I basically get I is equal to log of x. That you agree? So if there is a number x, then x has basically log base 10 x number of digits. So therefore I'd say like whatever is the highest number in the array, then d is basically log of that highest number. So your d is almost the same as n log x being the highest number. So bucket sort is more generic. Right? Like bucket sort just says, hey, look, my fundamental is you can create any sort of bucket you want. You can create a bucket of all numbers from 1 to 100, all numbers from 100 to 1000, all numbers from 2000 to 3000. You could create any bucket that you want, as long as it covers all range. You put numbers in the bucket where you know that every number in bucket 1 is going to be smaller than every number in bucket 2. So you just bucketize these numbers, you sort them separately, and then you append. That becomes bucket sort. It is very generic. Radix sort is using bucket sort in one way. Why this type of bucketing works? Going for all positions instead of just MSB or LSB. Let's say if you just go for MSB, there wherever two numbers have different MSB, most significant digit, there, I mean, you probably can only do with most significant digit. The problem is there will be a few numbers that will have the same most significant digit. In fact, there are only 10 possible most significant digit, right? So if you have, let's say, 1000 numbers, then on average, you will have 100 numbers in every bucket, right? For example, here as well, I had 950 and 923. They'll all go to the 9 bucket. Now, how to actually decide the ordering between these? In fact, if you have a lot of numbers in the bucket, then how do you figure out the ordering between those? That is not clear. So therefore, you can't decide only based on most significant digit. You'll need to somehow sort these guys within the who have the most significant bit as 9 as well, right? Internally, you'll need to sort them. So there are two ways. One is like you just say, I'll bucketize based on the most significant digit and I will sort each bucket, right? So what happens is if I had n numbers, then on average, each of the buckets will have n by 10 numbers. To sort them, I'll take n by 10 log n by 10 and I'll have 10 such buckets. So I'll finally multiply by 10. This will give me n log n by 10, which is the same as n log n. So I end up reaching the same algorithm which I have anyhow done before. This does not seem to be an improvement. So therefore I said, like, can I improve further on it? And there we said, maybe if instead of saying that we'll sort the numbers in the same bucket, if we could do bucket sort multiple times in a way where at the end of it, all of them would have been sorted, then that would be nice. So I say, you know what, like for the sorting based on the most significant bit, one thing is if I can somehow reach a state where numbers with the same most significant bit, they are already sorted in some way, that would be awesome. But to sort the numbers with the same most significant bit, for example, if you remove the most significant bit, you'll need to sort them by the remaining bits. There also, if you just again break it down recursively, you'll reach the same state. Like you'll first have to sort based on the least significant bit, then the least significant and most significant together, and then the last 3 together, last 4 together, and so forth. In Radix, you have log base 10 of not the number of elements. I mean, so in n log n is number of elements. This is log base 10 x, which is the highest element in the array. This is not the number of elements. This is highest element in array. Two different things. But yeah, I mean, in cases of log n, if you have, let's say, 1 million entries, 10 power 6 entries or 10 power 7 entries, the log n is typically 20, 22, 24. In the case of numbers, the number of digit is probably still 8 or 9. So it can perform twice as faster. If max is less than n, go for radix sort. That I wouldn't say. If your log of 10 max is less than, in fact, significantly less than log n, then go for radix sort. Okay. In case of integer, we could use radix. That's why I said, like, if your log of max is less than log of n, you could use radix. That might run just slightly faster. Even if you go with bits, yes, you will eventually end up sorting. Just that the number of iterations will be more. All right, let's move to the next problem. Imagine you're given a bunch of numbers, which are not sorted, by the way. So let's say you have 5, 8, 3, 1, 6, some numbers, right? And you've been given this array that you cannot modify. So this is a constant array, cannot be modified. Now what you need is that if this array was sorted, let's say if this array was sorted, the numbers would be 1, 3, 5, 6, 8. Actually, let me change the numbers a little bit. Let's say this number was 7, right? If this number was 7, then the numbers would be 1, 3, 6, 7, 8. And then in the sorted array, if you were to look at adjacent difference, the difference here is 2, difference here is 3, difference here is 1, and difference here is 1. There you have to find out what is the maximum gap between the numbers when the array is sorted. In this case, the maximum gap is 3. So you say the answer is 3. So given an array, how do you find this maximum gap if the given array is constant? And obviously, like, one answer is you make a copy of this array, you sort the array, and you look at the adjacent differences and you take the maximum of that, which becomes time complexity order of n log n, space complexity order of n. Can you do something better than this? I'll repeat the question once more. You're given an unsorted array. The array is not sorted. What you have to find is if the array was sorted, and if you looked at the adjacent numbers differences, what is the maximum difference you can find? What is the max gap you can find?